A couple of guys from the NSA Playset want to stand in front of you and talk about PCI Express. Joe and Miles, give them a round of applause.
Hey, how's it going? Who here went to Mike Osman's RF Retroreflectors NSA Playset talk? Okay, who went to Josh Jatko and Teddy Reed's I2C implant talk? Who went to Dean and Loki's GSM talk? Okay. Who here bought any NSA Playset kit from the vendor village? You don't have to say if your employer sent you to buy one for research purposes, you know. This is Stupid PCIe Tricks featuring the NSA Playset PCIe. It didn't really start out as a NSA Playset talk, but it fits right in because this is a capability that they've got to have. It's got to be on one of those pages that were redacted or missing. Who am I? Joe FitzPatrick. I have an electrical engineering education with a focus on CS and InfoSec. I spent 8 years doing security research, speed debug, and tool development for CPUs, including hardware pen testing of CPUs and security training for functional hardware validators. I also teach a really cool class, software exploitation via hardware hacking, aka sex via hex. So if any of you are interested, you should Google for that. Don't worry, it's safe. It's work safe. And our mandatory meme, if Joe fits, he sits. If you missed the hot tub at Tour Camp, you should go next time it runs in 2 years.
Hi, I'm Miles Crabill. I'm a current student and hardware newbie, but interested in computer science. And I met up with Joe last year and have been working with him for the past couple months on this NSA Playset PCIe stuff. So I didn't come in with much hardware experience, and I've pretty much been learning as I went. It's been a great time. And so I couldn't show this, of course.
So Miles has been great because he makes all my code look presentable. I'm a hardware guy. I'm not a coder. So a slight disclaimer. This is oh, did I put that? Yeah. I didn't do really good research. I didn't cite a lot of people. But there are tons of people who've done PCIe DMA work and other stuff. So yeah. The difference is that, you know, in line with the NSA Playset goal, we're trying to make this accessible and inexpensive. We want any 10-year-old to be able to start doing DMA attacks and memory dumps and lock screen bypasses. So Miles is going to give us the rundown of what the heck is PCIe, since even though many of you might know it, you might not know the next layer of detail.
Okay, so what is PCIe? Well, the answer is that PCIe is PCI. It's extending on this old specification that's been around forever, and it's for fast I/O, right? If you have a video card or something like that, network card, sound card, anything really that goes in an extension, it'll probably be on your motherboard, whether you're on a laptop, desktop. Most modern computers use PCI, and so this is how you get fast stuff going on the hardware level. And so there are also things that don't match up. As you can see here, they don't look exactly the same. However, PCIe is backwards compatible with PCI and PCIX. And so on the lower level, you have packets that are being transmitted across lanes. And so a lane is 4 wires. And when you see on a PCI card something like X4, X16, that's the number of lanes, and it corresponds to throughput. So the amount of data that you're able to transfer. Most video cards use X16 because they're transferring a lot of data. And PCI enables DMA access. So PCI hierarchy. The root complex is the highest node in the hierarchy, and pretty much everything else descends from there. So you can see this switch connected to the root complex, and then PCI devices will connect to the switch, and other PCI devices can be connected to other PCI devices. So you get a whole mess when you try enumerating this stuff. And so switching, this is the inside of the switch. From the upstream you have the bus, and then you have these virtual PCI to PCI bridges, and then these actually interface with the real devices that you have connected, the real PCI devices. And so the layers of PCI building up from the bottom, you have RX, TX, and then the physical layer of things, the logical side, electrical side, data, and then up to the transaction where you're actually working with packets. And I don't know how well you can see this, but this is the actual PCI spec. Stuff at the top like device ID and vendor ID is how you would identify a device. And so diving into that, we have LSPCI output, just checking out a specific device. So you can see this highlighted area is the vendor ID of a device. And so this is how you would check like the manufacturer. They all have codes associated. And then this would be the device ID. So this is like per specific product or family of products. And then the revision. So you can see that all of this is just right in these bytes that you can access through LSPCI. And this is the class something? Device class, yeah. So you can see that this is a PCI bridge that's 0604. That's just the code that's assigned to this type of device. And so enumeration, as I said before, it gets pretty messy because it's depth first traversal of the tree hierarchy, and everything like switches and PCI to PCI bridges will show up multiple times, and so any kind of like LSPCI VV output is just a headache to look at. It's huge. And so to Joe.
So, sorry, was I not supposed to talk on this one?
I guess not.
Okay, I'm back on. Routing PCIe. So we talked a little bit about like what PCIe is from a conceptual level. You know, the fundamental difference is PCI was 32 bits in parallel, a big fat parallel bus with multiple devices sitting on it. PCI Express is high-speed serial with differential signaling, right? So when you route high-speed signaling with high-speed differential signals, you have some rules you need to follow, okay? So if you wanted to go and make your own PCI Express device, you have to follow the step-by-step, complicated, mandatory, and inflexible rules of routing PCIe. And you have to follow every single one of these, right? Number one, route your pairs adjacent and roughly equal length, okay? That's pretty much it. So they made this spec to make it easier for designing boards, because routing 32 lines in parallel along with a clock, they have to all be equal length. That's a pain in the ass. So all they said is, okay, we'll do each pair on its own, TX pair, RX pair. As long as each pair is the same length, the next lane over could be a different length, the next lane over could be a different length, which really works well when you have a long card. It doesn't matter. All that is taken care of by the physical layer of PCIe. There's some specs, right? You have to have board traces. They're supposed to be 12 inches or less. Cards are supposed to be 3.5. Total of 2 chips on one board is supposed to be 15 inches. And if you follow these rules, your board might work. And if you don't follow these rules, it might still work. So PCI Express 1X, the lowest common denominator, is 2.5 gigahertz TX, 2.5 gigahertz RX, and there's a 100 megahertz clock that is a common clock. And that's actually optional. The device can actually generate its own clock, and it depends on the system, depends on the device. You can deal with that clock, but we'll throw it in there just for because we have room. So if we wanted to make a cable to connect this, like what do we need, right? We need something that can do high speed. And PCI Express specifies actually like external cabling, and it's really expensive. But I don't like expensive things because I'm cheap. So this is a cross section of a USB 3 cable, and if you look inside, you've got the red and the black are ground and VCC, right? The green and the white are your old school USB 2.0 wires, right? And then those are designed to go up to 480 megabit, right? That's what USB 2 was. And that's plenty to carry our clock. You then have these two little pockets, the red, blue, and the purple, orange, and those hold your high-speed lanes. And those go at 5 gigahertz, right? So we have this cable. We can get them for a couple bucks at pretty much any store, and they carry exactly what we need, right? They carry 5 gigahertz, and 500 megahertz. It's actually more than we need. So I threw together this little PCB. It looks like a PCIe card. It looks like there's a dotted line in the middle. That's because I'm cheap again, and you can get a 5 by 5 centimeter board for one price. And I wanted 2 boards, but I didn't want to have to pay for 2 boards, so I just put them on the same board. So you can cut it in half if you want, or just use it as is. You can see those red and blue lines. Those are the top and bottom layers where I just connect the wires together. And I actually did a really bad job of this, so if you do your own, like for production stuff, do your own. You can actually buy these pre-made from several manufacturers on eBay and AliExpress and other places in China. But that's no fun, so I made my own. This is what the board looks like, and I put the cool silk solder mask, silver lettering, because that's really important when you make a PCB to have your logo on there. I call it PEXternalizer, PCI Express Externalizer. And there's the board cut in half for the other end, and assembled populated board. You'll notice there's a 1X PCI Express socket up there, and the end looks kind of munged up and molten. That's because I just got my soldering iron and ran through that to open it up so I could put a 16X card in. So here's a quick screenshot. Basically, I plug a PCI Express wireless adapter in, and bam, it's connected, it's running, and I can connect to wireless networks. Woohoo! That's all well and good, but that's kind of old news. Like, what else can we do? Well, what devices can we add PCI Express to that don't generally have it? So, have you seen this? Intel Galileo. It's an Arduino board, but it actually has a mini PCIe port on the back. So that sounds cool. What can we do with that? It's supposed to only work with Wi-Fi adapters, but that's no fun. Anybody can plug a Wi-Fi adapter into an Arduino and make lights flash, because makers make, oh, I'm not wearing that shirt. Oops. Makers make lights flash. Hackers make other people's lights flash. So, so I made another version of the board. This is a mini PCIe version. And, how's time doing?
211.
211. Okay, you want me to show you pictures? You want to flip over? I'll actually show you how are we going to do this? Oh, there's the webcam. Oh, whoa. So we've got here a nice, oh, there. Upside down graphics card backwards. We've got our Intel Galileo, right? And flip on the other side, we've got our mini PCIe card with that USB header. Again, it's not USB. It's just using a USB header and USB cable because they're cheap. At the other end, I have the populated thingy-do, which has a little power regulator. And we don't actually have the power supply and the cables and an extra VGA to hook it all up and show you. But basically, we plug...
Oh, sorry.
Stay still. Plug. Oh, I'm looking at the screen. It doesn't.
Oh man.
Woo! Is this anybody sick yet? Pop it in the slot.
Oh God. All right,
there we go.
All right.
So you got that, right? I'm showing you guys here. You guys can see. There we go. Is it more than 12 inches? Yeah. Do you think it still works? Yeah, it still works. So some screenshot. Oh, here's the remote. Whoa. There we go. There's the thing. Actually, when I tried it out, I used a much bigger graphics card because, bigger is better, right? So wired them up. You see that tiny little Arduino and that nice big burly graphics card hovering over it. And if we hook it up and we look, I had to do a little bit of custom building of crap, which is annoying because it's software and I hate software. But if you do LSPCI, same tool as before, it's running on the Galileo board already. You see a whole bunch of 8086, 8086, 8086, 8086. Anybody know whose vendor ID that is? Okay. And then all the way down to the bottom, there's that 10DE. Who do you think that might be? NVIDIA. So, we're just kind of sneaking in there and put NVIDIA in bed with Intel a little longer. And here we go, hooked all up. I hooked it up to my full HD display, just to say, hey, look, I have X running. Whoop-de-doo. There's no keyboard input or anything like that, but at this point it's a software problem, and I'm a hardware guy, so it's someone else's problem, right? So let's move on. The other device I played with, I don't have it here to show off. It's not fully working yet. There's this guy. It's a Pogo plug. It's a network attached storage device. It's got an Ethernet port and a USB port, and you plug your hard drive in, and it shares it for the whole world to see. But they don't tell you about that part. And if we look at two versions of the PCB, this is the cheap one. This is the expensive one. The big difference is in the upper left corner, there's an extra chip. That's a USB 3 chip, because you want USB 3 on your very slow network attached storage device. The way it's connected is PCI Express. So if you see on this one, those purple wires on the left-hand side, those are my PCI Express lanes. I got TX and RX pairs, and then I've got a clock line. And the keys don't really come out so good. I took these with my phone through my magnifying glass. But you see on the left, we have a couple tiny little resistors that are, I can mouse over it. Can you see the mouse cursor? You can't. Oh, no. Oh, you can. So you see right there, there's a couple resistors because there's some resistive loading you have to put on the clock lines. And then over here, they're still very small, but you see that little brown spot right there and there? Those are capacitors that are soldered to the tip of a USB connector, right? And then the wire is soldered to the other side. And it looks pretty fancy, and like a year and a half ago, I sucked at soldering, and I still do. But, you just find a friend who can do it. Thanks, Kenny. He's not here, but, those of you who know Kenny, know he does good work. So again, that goes out to a USB connector, which is, same pin out as this shenanigan. So my plan there is to get that working and see if I can compile those drivers for ARM instead. So introducing slot screamer. This is where we get into the NSA Playset side of things. Uh-oh, it says it reset our timer. Oh, it's 2:16. We're good. Introducing slot screamer. Slot screamer, it's in all caps because it's cool to have things in all caps. I've had some critiquing because the name sounds too good. It's not random and silly enough for NSA Playset because it actually is a device that goes in a slot. So I apologize. Again, I mentioned before I didn't do a lot of research or citations, but I was at Black Hat and I saw this awesome slide, which is from Steve Weiss, talking about protecting data in use from firmware and physical attacks, which is kind of what we're about to do. So I figured I'd throw his slide in here. Thank you to all of these people for all of the work they've done, because I wouldn't be doing any of this if they hadn't done before me, including all the citations. It was also really cool to go into someone else's talk and see my name on it, which I was like, woo! This is my first time talking at DEF CON, so it's Miles' first time too. So I'm glad we could have our first time together, Miles. So a lot of people are playing with this, doing PCI Express attacks, but a lot of them are using FPGAs. FPGAs are expensive and they're difficult and they're hard, and you have to download like 20 gigabytes of software to get them working, which who cares about that software stuff, right? So I looked around and I found this cool little ASIC. It's PLX Technologies makes it. It's a USB 3380. It's a PCI to USB bridge. It works as a device. A USB device port. So you can plug this card in your system and load some drivers and make your PC look like a mass storage controller. You can also use this configured differently and make a PCI Express device work over USB. So you can have a USB attached graphics adapter, right? This is a block diagram. One side you have PCI Express, the other side you have USB. That's pretty much all there is to it. But every chip that is configurable in ways that they didn't really intend, so that's what I did. They've got this PCI out endpoint. An endpoint is something that shows up from USB, right? So from USB, I'm going really fast, aren't I? Am I going too fast? I apologize.
We have a lot of slides.
We have a lot of slides. What are we on? We're on 49 of 92. Okay. So we're actually going a little fast. So let's slow down. PCI out. Okay.
Breathe in, breathe PCI out.
It's actually good because I thought we weren't going to have enough time and I was going to tell them to go away. But since you came at the right time, how's it going?
Good.
What's all this?
So we heard this track was going a little bit fast, so we thought we'd come mellow things out a bit. That's why we're here.
Thank you.
How are they doing? I gotta say though, all right. Well, I guess he really wants you to slow down. The slides, they're a bit of an eye chart there, although when you had that picture of the device up, the board, I was getting all the detail on that. Yeah. I got it.
Excellent.
All right. New speakers at DEF CON.
Cheers.
Cider.
I did that for all of you. I hate whiskey. Hold on. Thank you.
You're welcome.
Can I continue now? So, PCI out endpoint. This shows up on the USB side of things, right? And this is basically a packet format. We need to write a bunch of bytes from USB to this guy, and it actually fills out what's called the PCI master control register and the PCI master address register, right? What happens is when these registers get filled up, the chip, this guy, what he does is he receives that data from the USB side. He takes it into his little hardware stuff. Don't worry about it. It's hardware. You guys wouldn't understand. And he generates a PCI Express packet, which goes out over PCI Express to the root complex. The root complex processes it, does whatever you want or whatever you told it to, and sends back a response. So what we can do in this, once we've enabled it, so again, this comes out of the spec, sorry for the eye chart. If we look down here, we have this little endpoint enable bit, right? So you'd think something silly like this would be off by default, but oh, actually, look, others equals 1. It's on by default. How convenient. Which makes sense because if you look at the drivers for this device, the standard Linux drivers for USB Gadget FS, which lets you use this as a device port so you can turn your computer into a mass storage controller. They have this little section where they explicitly disable these dedicated endpoints. And I think in another kernel version they have like, for security reasons, we need to disable these endpoints, which is great because I like when I see things like that in documentation. And then I talked to PLX field service engineers asking about this, and they're like, oh yeah, we don't really do that. That's not what it's for. But you could try it. It should work. So didn't really say what would happen if I turned it on in this mode, but I heart undefined behavior. So is that sticker still on there? Good. At least it's not on my shirt. Thank you, Mike, for the shirt, because my X key score goes to 11. So they disable it. Anyway, I'm still not going too fast. Good. So if we look in, I already showed you this. Basically, here are the 3 registers again. If we look inside, this is the PCI master control register. Basically, what we do is we need to write bits that are going to end up in here and do these things that it says. And this bits 5 to 4 is 2 bits. We can basically say, do we want to do a memory read, a memory write, an I/O read, an I/O write, or a config read or a config write, okay, or a PCI Express message. Let me explain for a second what each of these are. Memory read and memory write is exactly that. PCI Express devices need to have memory mapped so they can read and write to buffers in main memory. So if we want to read from memory, we can do that. If we want to write to memory, we can do that. I/O read and write, really nobody uses this anymore. It's all legacy stuff, but might as well try it because all the legacy stuff wasn't tested as well as the new stuff. Configuration read and configuration write, those are when we're actually directly accessing PCI Express devices. So when you enable things on your graphics card, you're doing a configuration write to a bunch of registers on your graphics card. That's what maps to the table of vid, pid, class codes and stuff that Miles talked about briefly before. Another eye chart. Basically, this is all well and good, but we need to have this device just work. We want to just plug it in the socket and have it start doing stuff. We don't want to have to deal with loading drivers because, who's going to load drivers on a TAC machine? No one clicks on silly things, right? So we can modify the firmware, and I can't even read this, so you probably can't either. Basically, there's a little chip on the PLX board. Where's my board? Anyway, that will hold configuration data, and when the chip turns on and powers up, it will read this data and set the registers right. And you'd think, okay, so a lot of work put into this custom firmware that I made. I've been talking all about it. You think I did a lot of work? I'm lazy. It's these how many bytes is that? These several bytes. That's it. That's the contents of the EEPROM. And to decode it for you, for those that don't speak XXD, basically we've got 2 registers I wrote to. The first register, that 497000000 is basically the other way around, 00007049, right? That basically is the contents of the basic, what ports to enable register, and I set the bit to enable USB. So when the device turns on, first thing it does, enable USB. Okay? Second thing I do, this E414BC16, that's actually the vendor ID and device ID of the Broadcom secure digital card reader, right? Because secure digital card readers, everybody trusts them. If I tell them I'm one of those, they'll turn everything on. They'll turn on Busmaster even if they don't need to. So that's pretty much all, right? That's all I did to configure this chip to make it do my bidding. So let's attack via PCIe. Is this where you take over?
So as Joe said, who wants to load a driver, right? But But then we have this whole category of target-side software where we have to like make sure that the target has all the stuff that we need in order to get our attack rolling, right? But no, nothing. And so on the attacker side, we actually do have some stuff. So what we're doing is we're using PyUSB, which is a nice Python library for interacting with devices over USB, to interact with the PCIe endpoints on the slot screamer, the USB 3380. And so this is just a little snippet of code showing a dirty PCIe memory read and write in PyUSB. So at the top you can see the read. We're actually making a packet to send, and you can see this 0xCF. I think the F is what denotes a read. And then down at the bottom here you can see the 4F, or maybe it's the C. But the 4F means that it's a write. And so now we have a demo.
So you get the video. So instead of doing the whole switching screens and everything, you want to get the webcam up? Yeah. Basically, we've got this little device here. It's a NUC. Intel makes them. They're tiny, and they compute. And so what I did is I basically hooked up the device to this little board, and through the attack device. Whoa. Hey! Oh, upside down.
We want to give you all motion sickness.
So, woo! Oh no.
It's still on my screen.
No, I stepped on the power strip, which is your flaky power strip.
I saw a light, and then it went away. Does this come back on by itself?
Here we go. So I got to reboot my NUC. Luckily, it boots fast. Are we still on? Oh.
Let's see.
Sorry, please.
Photo booth.
I won't step on it again, I promise. What time is it? 2:27. Oh, ready? No.
It's not.
Oh, you know what we need to do? We need to unplug and plug.
Plug and replug.
Yeah. Something. That's not it. Wait, that is it. You just need to smear your screens.
Yeah.
Ah, I didn't recognize the picture. It's not my desktop. I never get around to changing the default desktop anyway. There we go. Can you see that?
No?
Wait, there we go. Patience. Okay, so basically I'm using Python. Yeah, you hold it, so I'll stay away from the power strip and step back from here. Can you guys see that? It's backwards, isn't it?
Yeah.
I'm sorry. It's a crypto challenge. So what I'm going to do, basically I wrote the little sample utility, so I'm going to init PCI, and I'm going to hit enter, and it actually worked. Woohoo! So what it did is it actually went and initialized the link from this PC to the attack device over PCI. It found two endpoints, the 0x0e and 0x0e out, which those actually line up to what I showed you in the R chart before. I'm sure you all wrote those down. And then I'm going to read PCI. And so I give it an address and how many bytes to read, and right there I just get a whole bunch. It's Python software. You see F's and zeros and B's and some strings and stuff. So yeah, I just read memory off of this guy over PCI. Woo! It's not the greatest demo, but you know, we're getting there. So what's next? Are you?
Software.
Software.
Okay. And so, how many of you have heard of Inception? Not the movie. Okay, that's a few. So there's this cool utility that Karsten wrote, and what it does is exploit the DMA features of FireWire to basically patch some host. And you might be able to see here there are some selections that you can choose, targets with signatures, so it can identify based on the signatures certain operating systems and inject code into it. For example, like the OSX one makes all passwords nothing. And so what we have is, instead of Inception, we have into PCIe, which is an extension that we're...
It's an anagram.
I didn't know that. Yeah, so we've extended Inception to PCIe, and we're still working on it, so ironing out bugs and that kind of thing. But that's the goal.
Yeah, so this is right from Karsten's documentation, and basically what we're doing is we're hopping through memory and looking for the page that contains the, whatever authenticates your password. You do the whole process, authenticate password, and you say, yes, you got it right, no, you didn't at the very end. So it has a signature, which is what's listed as the chunk of memory data. It looks for that signature at a certain offset within every 4K page. So it doesn't matter if you have ASLR or anything, because within a 4K page, it always ends up the same spot. And then you go and patch it. And the patch goes at a certain offset. So basically, you just change the jump to a no-op or something like that, and you bypass. So when you type in blah 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 blah, enter, no matter what blah 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 is, even if that's your password, it goes through and lets you bypass the lock screen. We didn't do any work there. We didn't do any of that work. Other people have been doing this FireWire stuff for a long time. Okay, yeah, don't clap, don't clap. So we just ported it to this PCI Express native interface, which is great because you don't require drivers, right? FireWire vulnerability required that the host operating system install drivers. Oh, I'm supposed to talk this later, aren't I? Yeah, sorry.
So if you see here, you can see the chunk, which is actually the signature that you're trying to look for to identify, in this case, OSX 10.9. So earlier this week, Joe and I were in our hotel room taking dumps together. As you can see, from this little highlighted into PCIe business, and all of the slot screamers on the desk. So I decided, after taking all those dumps, to do some stool analysis. If you've heard of volatility, it's a really cool memory analysis framework. And so this is the D-message log of the attack, straight off of the victim. You can see my solarized color scheme there. So at the top, you can see the Thunderbolt first being recognized when plugged in, and then some PCI configuration going on. And I decided, hey, why not do some more analysis, because volatility has all these nice scripts. And so this is just another dump. You can see this is a Mac that we're dumping. You have some com.apple.something something something, and various other.
I was looking around too through the files, and I found some of Miles's cookies in his dumps.
And again, you can see here we have some machine info. I don't know what that major version, minor version business means, but I'm running 10.9.4 OSX. And I actually have the perfect amount of memory, 4 gigs on this machine, not for actually using things, but because these kinds of attacks are a little bit limited, because PCIe is limited to 32-bit addresses, and so we can't actually go over that 4 gig threshold. However, if you know what you're doing, 4 gigs is enough, is our assessment.
So how many of you guys know what Thunderbolt is? It's fun stuff. So it's basically PCI Express outside of your system. Kind of that whole USB crap, but without the sketchy boards and stuff. There's really, when you have Thunderbolt, you have 2 chips. This is straight from the Thunderbolt device driver programming guide. You have a chip inside your Macintosh, and you have a chip on your device. And they basically, the chip takes PCI Express in and DisplayPort in. They crunch it together into some other physical layer, really fast transport mechanism. And then the other side, it extracts what it needs to, right? And you can also even pass stuff through. So you can connect a DisplayPort to something else daisy chained along the end, or fun stuff like that. So of course we tried plugging our device into a PCI Express Thunderbolt enclosure. And in line with the NSA Playset, we decided to give that a new name. So Halibut Dugout is the slot screamer when inserted into a Thunderbolt enclosure. Okay, and you'll see the little logo for Great Scott Gadgets. Mike Osman was awesome. He sent me a bunch of hardware when he heard what I was working on, and that kind of motivated me to keep working on this. So thank you, Mike. The DIY. I'm forgetting what slides are next. DIY. How to do it? Yeah, I'm just in my mind. There's a gap there. So again, we're talking about DIY. People have been showing off these DMA attacks for a long time, but they're kind of inaccessible. They didn't give full disclosure of exactly how to do it, or their code for the FPGA or anything like that. So in line with the NSA Playset, go to the NSA Playset. There's a little page. Click on there. Slot Screamer. We're going to have all of the utilities, all of the firmware available for you to download and do this yourself. The hardware itself is this. Right now I'm using a reference board. Don't even have to solder to make this work, right? You go and buy this reference board from this sketchy company in China, hwtools.net. I sent them thousands of dollars and they sent me cards and they've been pretty reliable, and I've talked to their tech support a few times and they're very good with that. So that's the device. It's got the chip on there, pops in a standard PCIe slot. There is a little bit of hardware hacking you got to do. You have to go and find a jumper. Do you guys remember what jumpers are? And you have to put it over that first set of pins to connect the EEPROM with that chip right there. And then you have to go and you have to flash it yourself. We sold a bunch of these in the vendor area yesterday, all pre-flashed and ready to go for all of you who wanted to go back to your undisclosed employers and show off what you learned at DEF CON. Again, all the software is going to be on the NSA Playset GitHub. We put it up there already. Did you make it unprivate? No. It'll be available very soon. But now that we've got all you basically enabled to go and dump people's memory and check out their dumps and modify and do all that stuff, what could be done to fix this, right? Part of the NSA Playset mission is like, okay, state actors have had this capability for a long time, forensics have had this ability. Now that all of you have this ability, maybe they'll actually fix it. And actually I started out with like a kind of an anti-Apple, anti-Thunderbolt slant to this, but it actually came out pretty good. In Linux, if you look for this busmaster enable bit, basically any device you plug in the system gets busmaster enable turned on. You're like, oh, welcome to the show. What memory would you like? There really isn't a software remediation for this, right? You can't just not load the Thunderbolt drivers, FireWire drivers like you could with the regular Inception attack. But what you can do is you can use an IOMMU. You guys familiar with virtualization? Yeah. How about virtualization of hardware? Right? So basically virtualization on the left, you've just got software VMs that run code and interface with an abstraction layer, right? And then on the other side, you've got when you actually use VTD or an IOMMU of some sort, where you can actually assign a device to a specific software VM. You can actually have two graphics cards plugged into your system, each of them running native drivers in a separate VM, and no one would know the difference because all that memory DMA access is remapped. So if you configure a VTD right, like Apple does 10.8.2 and later on Ivy Bridge and later, they actually configure VTD right, unless you go in and change your boot arguments and turn VTD off, which is good for demonstration. You can go and modify memory. So basically what it is like, why those limitations? Why haven't they rolled it back to Ivy Bridge? Basically, in my opinion, any system that has Thunderbolt should have VTD on to protect you against certain things. Any system that has an express card, any system that you ever leave anywhere you don't see that someone could open up and pop one of these cards in, you should be careful. Your operating system vendor should be providing and enabling this stuff by default. It's just important. So until then, though, what solution do we have? Right? Abstinence, right? Well, Miles, would you ever plug anything sketchy into your DisplayPort / Thunderbolt port?
No, of course not. Right?
Well, what's plugged in there right now?
It's just a VGA cable.
Where does it go? What's this? Oh.
Wait.
Oops.
You gotta screw this in.
Yeah, but I didn't screw it in, and then I would pull the power cord out too. So, I got 5 minutes. Okay, so absence. Actually, yeah. So Miles plugged in this little cable that looks pretty simple. It's like one of those stupid $30 Apple adapters. But actually, we look at the other end, and it's really just a Thunderbolt cable that's going to our Thunderbolt enclosure, which is attached to a adapter. So this is how you could basically build one of these yourself. We call this Alloy Viper. Right? We need a new name because it's a cosmetic change to a commercial product. And actually this one at the list price I think is $300,000? Maybe a little less if you buy them in bulk. Actually it's pretty pricey because that cable alone is like $50. So you take one of these Thunderbolt cables and you go to Radio Shack and get one of these modular telephone jacks and these little metal thingies and a ferrite bead. Thank you. I can push buttons now. And you go get some heat shrink tubing, open everything up, you thread your Thunderbolt cable through there, right? Close it up, get your heat shrink tubing, thread the Thunderbolt cable through that, put the metal enclosure on the end, and that's pretty much it. You basically you say, oh, here, I already got an adapter for you. Thanks for presenting. So apologies to Joe Grand, those of you who were here last. Yeah, apologies to Miles. That dump I did was actually not that NUC. It was your computer. I didn't find any cookies in your dump, though. You know, basically on the other end, you put a standard adapter. I'm using the laser pointer to point at the screen. I apologize. Right here, I could point at this one. Is this better? You know? No. Which makes me think someone should make a screen that receives the laser pointer and draws it on the projector. So, invention disclosure. You know. So pay no attention to the man on the bill behind the curtain. When you plug this in, it finds the DisplayPort to VGA adapter on the other end and just passes it through. That's what we've been presenting the whole time. That's why it stopped when I stepped on the power cable. Sorry. I thought I almost blew the cover. So some acknowledgments. This is an incomplete list. Thanks to all NSA Playset crew for putting together some awesome talks and working together on getting things up there and running. Karsten for his work on Inception. Again, he built Inception based on many, many prior works before his. Again, great Scott Jadgets. Thanks for motivating me to get this started. Thanks for Dean for telling me, oh, wait, you haven't submitted that to DEF CON yet? And I'm like, well, I haven't done any work on it yet. He's like, well, just submit it. You'll get it done. Don't worry. Snare and Sam Collinson, they did a talk at SysCan last year using an FPGA board, which is basically the exact same thing as this, but, you know, with an FPGA board that's expensive. And everyone else who I forgot to, and Miles for fixing my ugly software code. So, any questions? I have swag. What do you want? What's the question?
Glad you quit your job.
Yes, I am. Here you go, Jen. Here's your NSA Playset pin. Any more questions? Yeah? I don't know anything about the mitigations in Windows 8.1. So the question is, what mitigations are built into Windows 8.1? Is that? I don't know. I haven't tried yet. I haven't actually seen Windows 8.1 before. So. It's ugly. You want an NSA Playset pin? Sorry. Any more questions? Yeah.
Anybody that has questions can come to the microphone right here so everybody can hear the question as well.
Oh, well. Thank you.
So it doesn't matter what operating system they're running or anything because you don't need any drivers. You can just go ahead and...
Just plug and play.
Yep.
Yep, no drivers needed unless you got to figure something out on those Mac versions that we mentioned. So.
A couple of minutes for questions. Just tell them you take 2.
Is it 4 gigs because why isn't it 2 gigs? I mean, I thought it would be a signed integer.
Why 4 gigs? PCIe has 32-bit DMA natively, and that's just.
Can you offset it 4 gigs and do it again?
You can offset it, but you need to change a DMA offset, PCIe DMA offset register, which would require some device-side drivers or software. But again, you have access to the lower 4 gigabytes of memory. You can do a lot of stuff there, inject whatever code you want, and do fun stuff.
Thanks for doing this.
Yeah. I think we have time for 2 more questions.
Did you look into USB DMA? USB 3 has DMA.
USB
3 super speed has DMA.
Has DMA?
Yeah.
Does it require drivers, though?
I don't know.
Most likely. I don't know. So.
I'm more interested in the running the VMs with external PCIe. And so is the information you presented going to be up on one of the websites?
I'm sorry. I can't really hear everything.
Okay. I'm looking for the information building external PCIe connected to virtual machines that you discussed a little bit ago.
Before you answer, let me interrupt
using BTD?
Yes.
Let me just make an announcement. Somebody dropped their iPhone in this section. Everybody please check and make sure you have your iPhone on you if you have such a device. Go ahead.
I'm looking at building virtual machines, connecting external PCIe to them. And that's why the information you presented is going to be up on a website where I can get it.
I'm sorry. It's not you. I can't actually hear what people are saying in the mic. So, sorry. So, yeah.
I'm looking at building virtual machines, connecting external PCIe to a box, connecting it up into a virtual machine.
Right.
Can you talk about that?
Uh-huh.
I want to know information. I couldn't catch it all.
We'll talk offline. Is that good? So, yeah. I was wanting to know about how to connect external devices to a PCIe virtual machine with VTD. I think we have one more moment. Do we? Yeah. I guess not. No more questions? Okay. Thank you.